Hello friends, welcome to the Applied Polymer Rheology under the aegis of Polymer Process Engineering. Here we are going to discuss the rheometry. Now let us have a look about that what we are going to discuss in this particular segment. We will discuss about the sliding plate rheometer, then we will discuss about the cone plate rheometer, the parallel plate rheometer, the capillary and melt flow indexer. We will discuss about the extensional rheometry and the high pressure rheometer. Now, the rheometers, they are usually a specialized tools or mechanism that are needed for evaluating the fluid models and measuring the rheological parameters. Usually, they are necessary for the complex measurement in the using the research, this including the development and assessment of various flow models, as well as the analysis of a viscosity and a normal stress differences. Now, if we talk, and there are different type of rheometers available as on date, based on the uses, based on the fluid use, based on the various kind of other approaches. Let us talk about the sliding plate rheometer. Now, using this is the typical figure of the sliding plate rheometer. Here we are having the actuator rod, then we are having the transducers, cantilever beams, stationary plates. This one is the stationary plate, and here this is the spacer shine. And we subject the polymer over here, and this plate is moving one, and this is the linear bearing table. So, here the sliding rheometer, this is the simplest type of shear between the two parallel plates. Now, the two flat plates make this type of a sort of a rheometer, with the upper plate moving back and forth at the consistent speed, while the lower plate remains fixed. This is like this. Now, every streamline is straight and parallel to every other streamline. So, the shear rate can be given as gamma dot is equal to U over H, where H is the gap between the plates, and U is the relative velocities between the plates. This is the schematic of the sliding plate rheometer with the shear transducer. Now, the viscosity is calculated using the sensor measured shear stress tau. So, neta is equal to tau over gamma. This kind of a geometry can be utilized to study the orientation effect in filled system, which are very common in the polymetric system. Can be used in the fiber reinforced polymers and can be used in different type of molding operation, injection molding, all those things. Now, it is also avoids the non-uniform flow field of capillary rheometers and flow irregularities associated with the rotating rheometers. Now, the shear stress, this can be measured directly on a tiny section of one of the plates using the sliding plate rheometer and a shear stress transducer that is usually created to specify this particular purpose. It is also enabled the measurement of linear and non-linear viscoelastic properties over a broad range of shear rates by eliminating the source of inaccuracy in traditional sliding plate rheometers. Additionally, the transducer makes it easier to produce significant consistent transient deformation with the high strain rate. Now, as a result, measurement can be made of a wide range of nonlinear viscoelastic parameter, including the nonlinear relaxation modulus and the shear stress growth coefficient. So, it enables the generation of a large amplitude oscillatory shear. This experience, which was not possible with the rotating and the capillary melt rheometers. It can produce stable shear rates between 0.05 and 500 per second. Molten plastic, concentrated polymer solutions, raw elastomers and other viscoelastic materials, they are the better candidate for this particular system. Let's talk about the cone plate rheometer. This is the schematic diagram of the cone plate rheometer, this cone type of a structure. The primary and a secondary normal stress coefficient function as a function of temperature and shear rate are frequently measured using the cone plate rheometer. Now, it is the only rheometer that can carry out a comprehensive range of rheological experiments, including oscillations, ram, creep, and relaxation tests. Now, this particular figure depicts the cone plate rheometer's geometry as well as the proper filling. Now, to ensure that the gap is entirely filled and to account for the resin inflow caused by the Wiesenberg's effect, it is recommended to add extra melt between the cone and the plate. This is the fixed plate and this is the cone. The polymer's shear gap is the remaining space between the cone and the plate. The cone angle theta naught and the radius r establish the geometry. Now, different parameters they are measured, the experiment like cone angular velocity, the torque required to turn the cone T, tau, the total force normal to the fixed plate F, and the pressure distribution on the fixed plate as a function of R. Now, angle theta naught is commonly between 1 degree and 4 degree. Therefore, the shear rate can be thought of as constant for theta naught is less than to 3 degree, and it is given by gamma dot theta psi is equal to omega theta naught. If the torque acting on the cone and the plate are equal, then the shear stress can also be thought as constant and related to the observed torque. So, torque can be given as tau dot is equal to 3t over 2 pi r cube. Now, the viscosity function this can now be obtained from neta dot gamma theta psi is equal to tau dot theta psi over gamma dot theta psi is equal to omega theta naught 3t over 2 pi r cube. Now, by measuring the force F normal to the fixed plate that is necessary to hold the cone in plate, the primary normal stress coefficient function psi 1 is computed from the primary normal stress differential N1. So, the psi 1 can be calculated using this particular formula, that is psi 1 is equal to N1 over gamma dot square theta psi is equal to 1 over gamma dot square theta psi 2f over pi r square. As the melt moves towards center, the radial stress component inside it grow, increasing pressure. Although the normal stress or pressure distribution over the plate can be used to calculate the secondary stress coefficient function psi 1. Now, the accurate data collection is exceedingly challenging. However, a rough estimate can be made using this particular general principle, that is psi 1 is equal to 0.1 psi 2. Now, let us take example of a cone plate system. You need to determine the restriction of a cone plate system based on geometrical boundary condition. This can be the specification like torque T is minimum and maximum value is given 2 into 10 to the power minus 2 Newton centimeter, and the maximum is 20 Newton centimeter. Rotational speed is equal to 10 to the power is 2 per minute, and 10 to the power maximum is 10 to the power 3 per minute, and the plate radius is given, that is 12.5 mm, and the maximum is 25 mm, and cone angle theta is 3 degree and minimum and 6 degree maximum. So, the first, the viscosity and the shear rate limits, and this should be determined from the maximum plate radius R2 is equal to 25 mm and cone angle theta 2 is equal to 6. So, the rotational speed n gives the angular velocity of the plate omega is equal to 2 pi, and the minimum and the maximum shear rate of the cone plate geometry can be determined by gamma dot is equal to 2 pi n theta, and gamma minimum 2 pi n minimum over theta 2, which if we substitute this thing into 10 to the power minus 2, 180 degree 6, that is comes out to be minus 2 per second, and gamma dot maximum 2 pi and maximum theta 2 is equal to 10 cube per second. So the viscosity can be given as neta is equal to 3t over 2 pi r cube gamma dot. Neta into gamma minimum t minimum, this is equal to 3t minimum 2 pi r cube gamma minimum, which is equal to 3.2 3 into 2 into 10 to the power minus 2 over 2 pi into 2.5 cubes meter cube into 0.01. This is equal to 611. So neta gamma minimum T maximum is equal to 6.11 into 10 to the power 5 Pascal second. Now neta gamma maximum T minimum is equal to 6.11 into 10 to the power minus 3 Pascal second, and neta y gamma maximum T maximum is equal to 6.11 Pascal second. Now we can evaluate how the viscosity measurement is affected if the cone angle remains constant but the radius is reduced to R1 is equal to 12.5 mm. So the reducing the radius by half to 12.5 mm means shifting the viscosity to higher values. So according to neta 2 over into gamma dot t over neta 1 gamma dot t is equal to R1 over R2 cube. The shear rate range stays constant because it is unaffected by the radius. So finally, we can evaluate how the viscosity measurement is affected when the radius remains constant but the cone angle is reduced to theta 1 is equal to 3. Now reducing the cone angle theta 1 is equal to 3 means shifting the viscosity range to lower values and the shear rate to higher values. So if we take n2 over eta 2 over eta 1, theta 2 over theta 1 and gamma 2 dot over gamma 1 dot to theta 1 over theta 2. The parallel plate rheometer. Now this is the schematic diagram of parallel plate rheometer. The two parallel even plates make up the parallel plate rheometer, which is also referred to as the plate rheometers. Now similar to the cone plate arrangement, the upper plate spins while the lower plate is normally stationary. So this is the stationary phase and this plate rotates. This is the typical geometry of the parallel plate rheometer. Now to ensure the uniform flow throughout the whole gap, the distance of the gap between the plate is maintained as h, and this should be substantially smaller than the radius of the plate r. The shear rate increases with the distance from the rotational speed, and that is small r is in between 0 and r, which is a drawback as compared to the cone plate arrangement. And the shear rate gamma is equal to 0 at the center, r is equal to 0, and it reaches to the maximum near the edge, that is r is equal to r. The maximum shear rate at the edge is utilized to analyze the measurements. And now, as per this equation, the gap height h also influences the shear rate. So, the gamma dot r is equal to r omega over h. The maximum shear rate at the edge of the plate is given by gamma dot r is equal to r omega over h. Now, these equations illustrate the importance of the gap height. So, this is the gap height. Now, an increase in the gap causes a small shear rate at the same rotating speed, and this device can therefore accommodate a wide range of shear rates. The cone plate rheometer is more popular than the parallel plate rheometer for a variety of applications. However, the parallel plate system offers some benefits over the cone plate system. Although the parallel plate system has several benefits, the cone plate system is preferred because it offers a consistent shear rate in the conical gap. Let us talk about the capillary rheometer. The capillary rheometer is the most popular and the simplest tool for determining the shear rate viscosity in the processing range. Hagen and Paschali, they were the first to utilize to gauge the viscosity of water. Now, it is essential component and its essential component is a straight tube or capillary. The pressure driven flow in a capillary rheometer is non-homogeneous because the velocity gradient, also known as a strain rate or shear rate, is largest near the capillary wall and zero at the center. This is the typical figure. Now, the pressure driven rheometer can only measure the steady shear function like viscosity because they use the non-homogeneous flows. However, they are extensively utilized since they are easy to use and relatively cheap to create. Now, long capillary rheometer, despite being straightforward, give the most precise and pertinent viscosity data which is currently available. Now, here you see the anatomy of the capillary rheometer. There is a heater in this well insulated. These are the pressure transducers subject to the polymer samples which extrudates. Another significant benefit is that in contrast to other kind of a rheometer like cone plate rheometer, capillary rheometer have no open surface in the test regime. Now, as shear rates greater than 100 per second, the capillary rheometer may be the sole viable option for detecting the strain rate dependent viscosity of the polymer melt. Now, this is crucial for the procedures like mixing, extrusion, injection molding that involve higher rates of deformation. The capillary rheometer can simply be mounted to the end of a screw or a ram type extruder for online measurement due to their simple design and requirement for only a pressure head at the entrance. Now, this makes the capillary rheometer an efficient tool for industry. The shear rate range is limited to the shear rates greater than 1 per second because shear rates lower than this requires additional consideration for surface tension, gravity and friction between the piston and a reservoir. Approximately 10 to the power 7 per second is the upper shear rate limit or the moment melt fracture takes place. Furthermore, at those high shear rate, viscous dissipation might become significant. There are certain presumptions that are made in order to calculate the viscosity relation. The capillary has no velocity in the radial and angular direction. The polymer is incompressible and the flow is fully developed, steady, isothermal and laminar. So using the z component of the equation of motion in terms of stress tau, the capillary rheometer can be represented as per this particular mathematical representation, where dp over dz plus 1 over r dr d over dr r tau rz is equal to 0, where dp over dz is equal to p naught minus p l over l. Now, if we integrate the shear stress term, then tau rz is equal to p naught minus pl into r over 2l plus c1 over r. Because of this, because of the stress at the tube axis cannot be infinite and the constant c1 is taken to be 0. Let us talk about the melt flow indexer. The melt flow indexers are frequently employed in the industry as a quick and easy method of quality control, since the rheological properties of polymer are sensitive to even modest molecular weight changes. Additionally, the melt flow indexers are frequently used to spot the material degradation during the processing check for consistency in material qualities between the batches or in combination of virgin and regrained material. This is the typical anatomy of melt flow indexer. There we are having the capillary, the polymer, then the thermometer and the weight. All these things are very common in nature. This is a single point measurement is taken out on a ram type extruder or extrusion plastometer under the standard testing setting conditions unique to each polymer class. ASTM D1238 outlined the recommended process for determining the flow rate of thermoplastic using an extrusion plastometer. Let us talk about the extensional rheometry. The polymer processes like film blowing, blow molding, thermoforming, fiber spinning, foam generation, they are described by the elongational deformation rather than shear. Large extensional component, they are present in the flow near the flow front during mold filling as well as in the converging or diverging regions of dies and molds. Because of their high molecular orientation or the orientation of filler with a large aspect ratios, the regions of extensional flow have a significant impact on the final parts qualities. Now, this is the exploratory extensional flow geometries like simple extension, this is the squeezing, this is the sheet stretching. The extensional behavior of the polymer melt cannot be determined using the apparatus which you discussed in the previous section for measuring the shear behavior of polymer. Although practically every manufacturing process exposes processors to extensional flow, extensional rheometry is the least studied area of rheology. The most common modes of deformation that generate extensional flow, they are shown in this particular figure. Now, stretching a polymer rod at a high temperature is the easiest method to determine the extensional viscosity. Now, due to the rod's decreased cross-sectional area, when we stretch, then the cross-sectional area will decrease. The stretch rate must constantly rise in order to keep the strain rate constant. This uniaxial deformation is crucial for processes like fiber spinning and those requiring converging flows, the least understood area of rheology, and depends on the material's macromolecular structure. Let us talk about the high pressure rheometry. Now, similar to the temperature, pressure also affects the viscosity, whereas lowering the pressure or raising the temperature raises the viscosity, doing the opposite of those actions lower the viscosity. There is no extra equipment needed for the simplest measurement. Its foundation is either a nonlinearity of the pressure drop observed in a Bagley plots created from the capillary flow, or the pressure profile produced as per the flow in a slit. Now, here you see that different type of high pressure rheometers like enhanced exit the enhanced exit the pressure device, then pressurized capillary or slit dies, then pressurized drag flow device. However, it is challenging to analyze the outcome of this particular technique due to the intrinsic effect and the simulation impacts of the temperature, pressure, and wall slides. Now, the direct approaches which are shown in these three figures need specialized equipment to test viscosity at high pressure. The enhanced exit pressure technique shows in this particular figure. This uses a pressure chamber near a capillary rheometers to create a back pressure. Now, pressurizing the melt running via a slit or a capillary with either fixed or moving piston provides a different alternative. So, dear friends, in this particular segment, we discussed different type of a rheometer for measuring the viscosity. As we discussed that the rheological behavior plays a very vital role to achieve the final shape of any polymer, whether it is injection molding, compression molding, and all kind of polymeric operations. So, for your convenience, we have enlisted several references, especially pertaining to the polymer rheology. You can utilize those references as per your requirement. Thank you very much.